All right. Now let's look at this thing, acetic acid. How many of you have had experience with acetic acid in the last week? Okay, good. What's acetic acid? What's that? No. That's acetone, which is related to this. Acetic acid is actually vinegar.
What?
Vinegar.
Oh.
It's a 5% by mass, or by volume, I never remember which. Anyway, it's a 5% solution of vinegar. Acetic acid. Okay. So what does it look like? Well, if we were to draw the dot structure, I just love drawing dot structures. What are we going to draw first?
Carbon.
Carbon. So there's 1, 1, 2, 3, 4. How about the other carbon? Let's slap that on there. 1, 2, 3, 4. And what we kind of learned to do next was to put the oxygens on. Where are we going to put the oxygens? It looks like both of them are attached to the same carbon, doesn't it? And they are, in fact. Here's 1. 1, 2, 3, 4, 5, 6. And here's 1. 1, 2, 3, 4, 5, 6. Okay? And now we just have to put the hydrogens on. It would seem that one of them could go right there. And the other 3, probably there, there, and there. Anything else we need to do here? What is it? Yeah, this carbon's only got 7, and that oxygen's only got 7. Not that you can particularly tell by the way I've drawn it, but let's try a little better. Okay? Yeah, so what we end up doing is we end up taking that oxygen, that electron off oxygen, and that electron off carbon. And we'll make a double bond. Okay? All right. Now the real question Natasha. Yes. Here's the green stylus. I would like you to go up there and draw a circle around the acidic hydrogen. There are 4 hydrogens on there, so if you didn't know anything at all about chemistry, you'd have a 1 in 4 shot. Yeah. But which of those 4, which one is the most likely to come off? Would you like a hint?
I was going to guess someone else.
Excellent.
So,
What do you think, folks?
I concur.
You concur? You're smart. This one is, in fact, the acidic hydrogen. Now, part of what that means is, thank you, Natasha, once this hydrogen comes off, you're not going to get any of these others off. This is, even though this has got 4 hydrogens on it, this is still a monoprotic acid. The only one that can come off in the presence of a base is that one. Now, why that happens to be the case is a matter that involves some discussion of electronegativity that we're not going to get into just yet. But it has to do with electrons and how they're pulled between the 2 atoms and things like that. But this one, in the case of acetic acid, this is the acidic hydrogen. Most acids, especially if you see a formula for an acid that has oxygen in it, you may be almost certain that the hydrogen that comes off is attached to one of those oxygen atoms. Okay? Now, while we're on the subject of acetic acid and oxyacids, I want to introduce you to a special class of acids. A few minutes we've got left. What we call organic acids. Okay? And organic acids are simply acids that have a carbon backbone. In other words, they're primarily a carbon chain that has acidic properties. Okay? Backbone, for lack of a better term. Okay? Now, how can you tell if a carbon compound is going to be acidic or not? Here's the way you tell. There is what is called a functional group. A group of atoms that shows up in each case. That functional group is COOH. Or maybe it's written CO2H. Okay? This your book refers to this as a carboxyl group. I know. And that's fairly accurate, but it's maybe a little non-specific. My professors always referred to this as just an acid group. So if you see that in an organic compound, in a carbon-based compound, it's an acid, and there's your acidic hydrogen. If we were to go back and look at acetic acid that we just got done with, there's your group. That carbon double bonded to oxygen, single bonded to oxygen, which is in turn single bonded to a hydrogen. That's where the acidic hydrogen is. That's what makes vinegar an acid, is that combination of those four atoms right there. Okay? Let me draw two quick examples here. Butanoic acid, and I'm not going to draw the dot structures, I'm going to draw the structural formula. Butanoic acid looks like this. Also, when we get to organic chemistry, I'm going to teach you a shortcut where we don't usually write the hydrogens attached to carbon. We just draw a line to show that it's there. This is butanoic acid. When butter goes rancid, this is what is produced. The common name for this, before there was a systematic way of naming it, this was called butyric acid, which ultimately comes from the word butter. Okay? And then this one, benzoic acid. This one's really fun. Okay? All right. This one has 6 carbons in a ring, and another carbon off one of those carbons, and then oxygen, oxygen, hydrogen. Each of these these other 5 carbons, by the way, has a hydrogen attached. Typically we don't draw that, but it's there. While we're on the subject, the fact that these bonds alternate single, double, single, double, single, double, introduces the possibility of what? Thinking back to when we talked about bonding. Starts with an R. Resonance.